Hello and welcome back, everyone. It's actually one of my favorite sections today that we're covering. I'm calling this section vectors, vector spaces, linear combinations, dependence, and independence. And in fact, like the reason I'm using this slash for dependence and independence is that those are referring to the word linear as well. So it's linear dependence, linear independence. That's why I've used the slashes there. But let's just start out. This should set us up for the entire semester, actually. Today is the last two sections on sets, functions, maps, and complex numbers were kind of like preliminaries to make sure we had a solid background for what we're actually doing. And today is really where we're getting into what's considered the study of linear algebra. You can see that word linear showed up for the first time. So what we need to tackle here is kind of the definition of vectors. And I think a lot of you may feel like you already know what vectors are, but what you learned in physics or even other math is only a small fraction of the story. Okay, so a lot of people think about vectors as kind of like these objects where you have a big parentheses and you put some numbers in them, and you can add them together to do something like -3 to 5 or something. That's valid. That is a representation of a vector. But a lot of people like to pretend that, and I don't think they know that they're pretending. They actually think it's true that all vectors look like that. And in reality, only a small fraction of vectors actually look like that. They're the common ones we use because they're easy to manipulate and they work in 2 and 3 dimensions like the world exists in. But they're actually a small fraction of what the vectors that mathematicians need to work with are, and in fact, in quantum mechanics, the vectors that you need to work with are. So I'm gonna define vectors in the way that really they should be defined, but unfortunately, until now, you're not really allowed to define them otherwise because the world doesn't expect you to have the mathematical maturity to handle it. But I believe in you. I believe you can handle it from now on out. So vectors are not those objects which have parentheses and a collection of numbers in them. Those are representations of some vectors. What vectors are mathematical objects which have the ability to be two things. Number one, scaled by real or complex numbers or other algebraic fields. But for any sort of physical reasons, you don't care about the other algebraic fields. So we're going to say it's a mathematical object which has the ability to be scaled, which is multiplied, the same as multiplied. So scaled or multiplied by real or complex numbers or other algebraic fields, but we don't worry about the other ones. And secondarily, added together. That's it. Any mathematical object which satisfies these two properties is a vector. It does not have to be written as a vertical column with a parenthesis on the sides and some numbers inside of it. As long as a mathematical object has the ability to be scaled or multiplied by real or complex numbers and added together, it's a vector. So I'll say hence polynomials are vectors. What do I mean by polynomials? I mean functions of the form x squared plus 2x minus 3 or 2x to the fourth minus 3x cubed minus 1 or x to the seventh, etc. These objects are vectors. They definitely are not written as columns with parentheses on the sides. Now, why are they vectors? Why? Well, can I multiply them by a real number? Sure, why not? So I can take 2 times the entire first polynomial that I have there, which is x squared plus 2x minus 3. It has a well-defined meaning. The meaning is 2x squared plus 4x minus 6. I can do the same with the second one. I can multiply that one by pi if I want to. So the second one by pi, 2x to the fourth minus 3x cubed minus 1. If I multiply that by pi, I get 2 pi, x to the fourth minus 3 pi, x cubed minus pi. I can multiply the third one by square root of 2 if I want to, x to the seventh. And what do I end up with? What do you expect? Root 2 x to the seventh. Okay, so I certainly have the ability to multiply them by a real number. Can I add them together? Sure. Nothing preventing me from adding them together. Let's go ahead and add x squared plus 2x minus 3 to 2x to the fourth minus 3x squared, or 3x cubed minus 1. What do I get? I guess I get, let's just work top order down, 2x to the fourth minus 3x cubed plus x squared plus 2x. And minus 3 minus 1 is minus 4. Sure, added those together just fine. So yeah, you can add them together, multiply them by reals. You've got yourself a vector. Another example. Any real valued function. So, f of x equals e to the cosine x. G of x equals log root x squared plus 1. Can I multiply those by a real number? Definitely. Sure. Or a complex number, of course, but let's just do a real number. Well, 6 times f would just be 6 e to the cosine x. Negative 17 times g would just be negative 17 log root x squared plus 1. So those are both perfectly safe. Can I add them together? Sure. So what would f plus g look like? It just looks like e to the cosine x plus log root x squared plus 1. That's all you gotta do. It's still a function. So those are, collections of vectors, functions, polynomials. And the whole reason why we're working with vectors this entire course, quantum mechanical states are vectors. Now, this feels weird. What do I mean by that? Because these states are right, they correspond to measurements. So when I write down Schrodinger's equation, which is why I'm using it this entire semester, IH bar ddt of psi equals h hat psi. These psi's are vectors. And what do they represent? So psi represents a superposition of pure states and its coefficients represent probability amplitudes for each pure state. Now, you don't need to know what that means. You probably won't know what that means until you take a quantum mechanics course. I'm not really going to get too far into it in this class. But what you want to think about is if we've got a representation of probability amplitude, then what can I do is I can take one psi here, I can multiply it by, let's say I multiply it by 1 over root 2 plus I over root 2. And I can add it, so let's say you take one state, psi 1, and I add it to another one, negative 1 over root 2 plus I over root 2. Psi 2, I can take two of these and add them together, and it makes sense. Quantum mechanically. So the psi's themselves, the psi 1 and psi 2, they don't necessarily have numbers associated to them the way that you would expect. They correspond to true measurements. Like this could be spin up, and this could be spin down. That's not really like a thing that you have a measurement of, right? It's just spin up and spin down, or you don't have numbers associated to it. And yet you can still scale them. This is scaled by a complex number. Scaled by a complex number. And added together. So these are vectors. They just don't feel like it. And so we've got this notion of vectors that's just so much more broad than what we were used to growing up in physics or other courses. All we have to do is be scaled by real complex numbers and added together, and we're still a vector. Now with that said, we will use these vectors, A, B, C, plus D, E, F, equals A plus D, B plus E, C plus F, vectors a lot in this course. They are the easiest to develop intuition and theory about. However, they are not necessarily the most useful in all disciplines. Quantum mechanics and mathematics, these sorts of vectors aren't actually as useful as they are maybe in classical mechanics. So it's just good to keep in mind that there are other vectors out there that don't look like the ones that we will probably be using in this course. With that said, now let's talk about vector spaces. A vector space is a mathematical set which contains vectors. Okay, what are vectors? They're these objects, right? These objects which can be scaled and added together, along with all possible scalings and addings. Okay, and this is where set builder notation actually comes in handy a lot, because what in the world does this mean? It's a space which has vectors in it and all possible scalings and addings. It's like kind of confusing. So let's go ahead and use set builder notation. In set builder notation, I'm going to use a capital V. It'll kind of look like a Roman numeral. This will be my vector space. And it's going to be a collection of scalars, right? These are scaling coefficients, so C1, and then a vector, V1, plus C2, and then a vector, V2, plus dot, 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 plus Cn, and a vector, Vn, such that, so this is just a collection of scalings, and sums of vectors okay, and they're going to satisfy something, right? It's a collection of, it's set builder notation, so it satisfies something. So it's a collection of scalings, vectors, and sums satisfying C1, C2, dot, 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 Cn are real numbers or complex numbers. I'll say or C. Doesn't really matter. It's just the difference between a real and complex vector space. And each of my V1s, or V1, V2, dot, 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 Vn are vectors. You just define kind of a set of vectors that you're going to build from, this V1 through Vn. You start with that, as long as they're objects that you're content multiplying and adding together. Those are your vectors, then you grab these coefficients from R, you just add them all together, and that is your vector space. That's it. So it's really not too complicated to build these things. You should build them from scratch once you decide what you want your vectors to be. But then you know that this space is kind of like, it's kind of like naturally closed under these operations. It kind of fills everything up by doing this collection of scalings. So let's just look really quick. So with an example would be like the polynomials of second degree, also known as quadratics, right? This is like your quadratic equations. We call these P2, sometimes P2 of R if we want to give them real coefficients, but I'm just going to call this set P2 for second degree polynomials. Using set builder notation, what we have is C1 x squared plus C2 x plus C3, right? These really are all quadratic polynomials, where of course C1, C2, and C3 are in R, and of course x squared, x, and 1 are vectors. But of course they're vectors. These are just functions that you can add together, so certainly they're going to be vectors. So this is just like how you would construct some of these arbitrary vector spaces. But probably everybody's favorite, whereas these ones I've been referring to the whole time, for example, R3, the three-dimensional space, the regular three-dimensional space you all know and love, R3 using set builder notation is just vectors of the form A, B, C, such that A, B, and C are in R. But that set builder notation doesn't exactly look like the way I'd written it earlier. How do we write this earlier? We write it as A times the vector 1, 0, 0, plus B times the vector 0, 1, 0, plus C times the vector 0, 0, 1. Right, now it looks like A, B, and C are in R, while 1, 0, 0, 0, 1, 0, and 0, 0, 1 are vectors. So that's how you get away with R3 doing set builder notation. Okay, so what have I implicitly kind of done here when I've constructed these vector spaces? Is terms of the form C1 times a vector plus C2 times another vector were very common. These are called linear combinations. That is to say, I'll say i.e., given two vectors, v1 and v2, a linear combination is a third vector of the form c1 v1 plus c2 v2. So I should say v3, which takes the form c1 v1 plus c2 v2 for some scalars c1, c2, and r, or c. That's a definition of linear combination. It's just the fact that you take two vectors and you combine them, combination, linearly, which is just the process that we're doing here, to gain a third vector. So that's the definition of a linear combination. And in fact, what we see out of this is a vector space is a space which contains all of its own linear combinations. This is an equivalent definition of a vector space. So anytime you have a set that you're able to perform linear combinations on, and you take the kind of the overall massive set that you could possibly construct that contains all of its own linear combinations, that's what a vector space is. Let's look at a nice example of this. So we can do an R2, which these are going to be vectors 1, 3, and -1, -1. We can linearly combine as, let's do 2 times 1, 3, plus 4 times -1, -1, gives me, how do these work? How does scalar multiplication work on these, by the way? I didn't necessarily go over that yet, but I think everybody assumes you just distribute across. So I'm going to get 2, 6, plus -4, -4. And then how do you add things? You just add across and across. We end up with -2, 2. So -2, 2 is this particular linear combination of 1, 3 and -1, 1. Finally, I'll cover the definitions, the final two definitions. Of linear dependence and independence. We have that given a set of vectors, here's my set of v1, v2, dots, v, and a extra vector, we'll just call it v n plus 1, is called linearly dependent to the set if it is formed as a linear combination of all others in the set. That is, if vn plus 1 equals c1 v1 plus c2 v2 plus ... plus cn vn for some collection of c1 c2 ... cn. For example, the vector 3, -1, 1 is linearly dependent to the vectors 2, 0, 1, 1, 0, 0, 0, -1, 0, since 2, 0, 1 plus 1, 0, 0 plus 0, -1, 0 equals, adding across horizontally, 3, -1, 1. So that's a definition of dependence, and then we call n plus 1. The n plus 1 is linearly independent of the set v1, v2, vn, if it is not linearly dependent. So you just have to verify that it can't be written as the sum of the rest of them, and then you're linearly independent. An okay example of this would be that e to the x is linearly independent of x squared. This is the set x squared, x, and 1. Since e to the x is never equal to c1 x squared plus c2 x plus c3 times 1. There's no way that I can ever get a quadratic function to behave like an exponential function. So today's gotten a little bit abstract. We're definitely going to be working through a lot of what's been going on today in the next video, as well as kind of the rest of this semester. So if some things aren't clicking yet, this is the sort of situation where you just kind of stick with it, wait like a week as we just naturally encounter these objects over and over and over again. You'll build up an intuition for everything that I've said here. So if it's not clicking right now, wait a week as I just continue to talk about these, we keep experiencing it, then maybe watch this video again, and I think it'll make a lot of sense. So I'll see you in the next video where we'll do some applications.